stopped at the non-inverting amplifier, and we said that, okay, our objective is always to do what? To drive this V input to 0, right? So if we drive this input to 0, and we know that our op-amp looks like a big box with, an open circuit terminals basically, then it simplifies lots of calculation, and we can use what is called the summing point assumption here. So if our op-amp looks like this open circuit input, and which means that there's no current coming into the op-amp, this is an open circuit, right? And then the other thing that makes our life easy was, okay, if we're able to make this voltage between these two nodes 0, then I can close the loop around here, I can close the loop around here, and do some calculations, relate input to output using the currents flowing in these various resistors, right? That's the beauty of what we wanted to do. Otherwise, there's no way to close the loop here, because I have an open circuit, right? So I have an open circuit between these two terminals when I leave the op-amp by itself. But when I do this feedback, if I do the feedback properly, then I do what is called negative feedback. Doing what negative feedback means, it's feedback that drives this voltage difference to 0, right? So when the input source, when the source here was connected previously to the negative side, I brought in a negative value. When now the input source here is connected to the positive terminal, if I don't have feedback, what will my output look like? V output of the open loop op-amp is equal to the open loop gain multiplied by the input voltage at the positive terminal, which is Vi, minus the input voltage at the negative terminal, which is 0 in this case, right? So it's minus 0 in this case, right? So I have an open loop voltage equal to A, which is a large number, multiplied by V, which happens to be V input in this case, right? This difference is Vx. This is this voltage here, Vx, right? If I don't want, again, when we saw that, if our op-amp output is going to be influenced by its open loop gain, we just have a comparator, right? That will go saturate high, saturate low, because this A is huge. It's the open loop gain. So it's useless. It's only useful as a comparator. So we decided we want to do feedback. We saw that if I do some feedback, clever feedback, then I can make Vx equal to 0. How do I make this equal to 0? I add something here, right? So if I add something here, then I can make this equal to 0. So basically bring in something from this output here. If I bring something from this output here, if this output happens to be V input for somehow, if this output happens to V input, then what is the open loop gain? V output equals A times V input minus V input, so it's 0, right? So if I'm able to do that in a good way, then my op-amp output will not be affected by its open loop characteristics. It will be controlled by my feedback circuitry around it, right? That was the objective for the inverting amplifier circuit that we looked at before, and the same thing for the non-inverting amplifier we will look at now. So here I want to do what? I want to bring back a positive number, right? Because again, in open loop, the output will be A V input minus 0. It's a positive number, a large positive number, right? So I want to bring back, so the output is a positive number. So I would like to bring it back to here so I can subtract it from V input, right? So I can make Vx equal to 0. If I bring back a negative number, what's going to happen in this case? If I put the resistor here instead of here, what will happen? I'm bringing back a voltage to the negative terminal. I'm making this, the output will be A V input times, it will be another circuit in parallel with this, right? It's this circuit, this is a voltage source, and in parallel with it, it has some resistor and some output voltage, right? So the voltage that I'm feeding back is another positive voltage, so it will be A times some Vx minus 0 as well, because this terminal is still connected to ground with a 0 volt, right? So I cannot put a feedback resistor here, right? If I want to put a feedback resistor, I'm putting it where it will make or drive this Vx, the differential input voltage, to 0. So how can I drive this differential input voltage to 0? I look at the sign of the differential input voltage. The sign of the differential input voltage here is positive. It's this terminal's voltage minus this terminal's voltage. Before, it was negative. Before, it was negative. The voltage was on the negative terminal, right? So then when I brought the output, I can bring it, before it was negative, so I bring back this negative voltage to the negative terminal. It would be a voltage that will be reducing the input voltage here, versus here, it will drive this to 0. Right here, to drive this to 0, I need to bring back a positive voltage to this terminal. In the other case, I need to bring back a negative voltage to the positive terminal. Okay? Any question? Because if I bring back a negative voltage to the positive terminal, then the differential voltage is equal to what? That negative voltage minus the voltage that I have on my negative terminal. Right? Yes? No? Okay, is it clear, the feedback, or no? Sally? Is it clear that if I don't have this, what will the output voltage be? I don't have this. What is the output voltage? This is an op-amp, no feedback. So what is the output voltage? What is the output voltage of the op-amp? The op-amp equivalent circuit looks like this, and a dependent source that has a gain of what? This is Vx. The gain here is equal to A times Vx. And Vx is V input plus minus V input minus. So it's the voltage at the positive terminal minus the voltage at the negative terminal. What is the voltage in the positive terminal minus the voltage in the negative terminal? There's no feedback. This is connected to ground to a resistor, but there is no current flowing. So what is the voltage? The same as the voltage here, right? So the voltage here is 0. How about the voltage here? Huh? It's V input. The voltage here is V input, this V input here. So the value of Vx is V input minus 0. So Vx has a value. Of course, from our op-amp characteristics, our output voltage in open loop configuration, this is open loop configuration, there is no feedback. In open loop configuration, the output voltage is equal to A times Vx. So A is a very large number times, and Vx has a value. It has a value. So the output will be large. The op-amp output is being controlled or driven by its open loop gain in this case. We're okay with this? So now, if I want not to have this, because this is not useful for amplifying, subtracting, adding, it's only useful for comparing. Okay, this has a value, this value is greater than this value is less than this value. Because I look at the difference between the voltage here and the voltage here. If the voltage on the positive terminal is greater, my output is positive. If the voltage on the negative terminal is greater, my output voltage is negative. That's it, right? Like in the before, it was a negative. In the inverting application, it was just opposite. It was 0 minus V input. The voltage was a negative value, right? So the negative value was the difference between these two. So the output was a large negative value. Here, the output is going to be a large positive value. For me to make use of this circuit op-amp as something besides a comparator, I need to drive this Vx, this voltage difference here, to 0. So how do I drive this voltage difference here to 0? I need to put something here. Instead of having Vx equal to Vn minus 0, which is then going to be multiplied by my open loop gain to control my output, I need to put something here instead of this 0 that is going to be equal to V input. For example, I put something here equal to V input, then Vx will be driven to 0, then the open loop gain A is not going to control my op-amp's output. Actually, the op-amp output due to the open loop gain will be 0. Right? It's no longer the open loop gain that's controlling my output anymore. Right? So how do I do that? I have to put in a number here. Is this number, should I make it a positive number or a negative number? It has to be a positive number because it's V input minus a positive number. If it's a negative number, it's going to be V input plus something. So, which means that if I look at my output here, and I know my output is going to be positive from the open loop gain. It's a positive number. It's A times V input. So it's a large positive number. I take that large positive number, and do I feed it back here, or do I feed it back here? I have to, if I feed it back here, it's going to just change this value to something else. So that doesn't make sense. So I cannot feed it back to the positive terminal. So where do I feed it back? I feed it back to the negative terminal. If I feed it back to the negative terminal, it replaces this 0 with a large number. This large number, if I properly choose the value of the resistance, then it's equal to V input, cancels out the effect of this gain, the open loop gain, right? And makes Vx drives Vx to 0. If I drive Vx to 0, then I have the summing point constraint property that I want to see, right? That will help me analyze these circuits, right? The summing point constraint property makes these two, even though they're here, they are, it sort of looks like an open circuit, right? Which means that current is not coming in, but it also sort of looks like a short circuit, right? Because the voltage is 0, right? So it looks like an open circuit and a short circuit at the same time. So we don't want to connect the short circuit because people will get confused. So we leave it as an open circuit, but we write the voltage here is equal to 0, Vx is equal to 0, which means I know that I can find, and I can go around this loop. This voltage is equal to what? The voltage across this resistor plus this voltage Vx. This voltage Vx is 0. So now I know that if I want to calculate my input current here, it's equal to this voltage divided by this resistor, right? It's because of this Vx going to 0. The analogy is the same for the previous inverting amplifier case, except that my feedback has to be such that I'm driving Vx to 0, right? So it was being driven. The output was negative. So if the output was negative, I was driving back to the positive terminal. The output was positive here, I'm driving back to the negative terminal. Right? It's just the opposite. So go back and think of the way we described it today, and yes, sir. I can't hear. Yeah, I can trace it. Yeah. So let me expand so it's easier. This Vi is equal to 0. If this Vi is equal to 0, then I know that this is one loop here. This is one loop. This voltage here is going to equal this voltage plus this voltage, correct? And this output voltage is going to equal this voltage plus this voltage. Right? So now I've created something else. So now my output is not really driven by my open loop gain anymore. It's driven by the circuit that I put around the system, the op-amp. Right? This is the whole objective. Okay with this? Please try to go back to the inverting one and try to think of the same way we explained it today and apply it to the previous one. Okay? So last time what we did was we looked through this, looked at the non-inverting amplifier, and we calculated its gain for the non-inverting amplifier. I can quickly go through that again if you're interested. Should I go through that again in light of this new explanation? Okay. I'll go through it quickly. Okay, so we have our amplifier. V input is here, ground connection is here, I'll have here R1, right? Plus minus V output. So if I just do this, what is V output equal to? I call this plus minus Vx. Come on. Yeah, this is AOL open loop gain times Vx. And Vx is going to equal V in minus 0 because there is no current flowing in this branch, so this voltage here is equal to the voltage here. Like remember our Thevenin equivalent circuits, right? So useless because it's a very large number. So what we did was, okay, it's a very large positive number. So what do I want to do? I want to substitute with 0 with a large positive number so that it counteracts the open loop gain of the amplifier and makes my Vx 0. So if it counteracts the open loop gain, then it's as if Vx is 0. So I bring back, I measure this voltage, I take a part of this voltage and connect it here. So this I will call R2. R2, if I have a voltage here and a different voltage here, then the current will be flowing in this resistor here, right? So this R2 will have one voltage here, another voltage here that is less than this voltage that I have at the output, because this output voltage is equal to this voltage plus this voltage, right? Remember, this is a loop. Here, this here is a loop where output voltage is equal to the voltage across R1 plus the voltage across R2, right? So I took part of the output voltage, which is across R2, fed it back to my amplifier. If I do that, then I'm going to counteract this 0. I will have a number here. This number will be forcing this Vx to 0 if it's properly selected, and the op-amp is ideal, all of these things. And then in that case, the output voltage will be controlled by something besides my open loop gain, right? So how do you derive the input to output voltage relationship? Remember, our gain is equal to V output over V input. V input is equal to what? Right, sorry, in terms of, so I'll call this V1, the voltage across R1 I'll call V1. Do we agree that V input is equal to V1 since Vx is equal to 0 when I did the positive feedback? So V input is equal to V1. And now I know that since I have this Vx equal to 0 and I have these two resistors connected in this fashion, in this feedback fashion, then V output is divided amongst these two resistors R1 and R2. So V output is equal to, V1 is going to equal to, in terms of V output, going to be equal to V output multiplied by R1 over R1 plus R2, voltage divider rule, right? So, and V1 is equal to V input, so I have this. So V output over V input is going to equal R1 plus R2 over R1, or 1 plus R2 over R1. Okay? If I make R2 equal to 0, what is the voltage gain? Closed loop voltage gain, 1. Right? So I can make input equal to output. I cannot make it negative, right? I can only amplify the input or pass it, it's either unity gain or amplify. Right? So this is the voltage gain. Is this voltage gain dependent on our load? It will not depend. So if I change our load, is my voltage gain going to change? I look at the voltage gain equation. It does not include anything related to our load. So unlike the internal battery resistance that we talked about last time, if my battery has an internal resistance, right, R internal, and this is R load, and this is V battery, and this is my output voltage. if I change RL, the current will change, correct? If the current changes, then the voltage drop across this resistor will change. Then the output voltage will also change. We agree? So output voltage here will change if I change RL. So this circuit has an output impedance equal to R input. Right? If a circuit's output voltage does not change when you change the load, then this circuit has an output impedance of 0, because if the output impedance is 0 in this case, if Rin is 0, if Rin is 0, then is V output going to change at all if I change RL? Change RL. Does not matter. It's in parallel with the ideal voltage source. Right? Parallel with the ideal voltage. Change RL, nothing will happen. The output will always be fixed. So in this case, this is a circuit that has 0 output impedance. In our turn, in our op-amp discussion, it means that the output voltage does not change depending on the RL changes. If the output voltage changes with RL changes, then the circuit has some output impedance. What is this output impedance? It's equal to the impedance that's in series with the output resistance. Okay? But in our circuits, the way we look at it is, if the voltage, this is the output voltage equation. Output voltage equation related to the input. If output voltage will never change because of RL. RL is here, it does not even appear in our equation. Okay, so the output impedance of this is 0. Input impedance is equal to V input over this current, I1. Right? And this current is equal to this voltage divided by this value of the resistance, because we have a loop here. If I want to calculate the current that's flowing into this terminal, it's V input divided by this value of resistance. Any questions? We're okay with this? So we did this example as well where we made R2 equals 0. So we created a voltage follower circuit. So if you put R2 is 0, you're following your input. The output is equal to input, or the gain is equal to 1. Right? What's the benefit of this circuit? If my gain is equal to 1, why don't I just take my output and connect it to my load? Why don't I do that? Remember, the op-amp is supplied by a power supply. Right? It has a power supply that is supplying this current. Remember, there's a voltage source inside this op-amp. So the current that is flowing in the output is not due to the input at all. The input current is limited by the input impedance, which is very high. So very little current is coming from, actually ideally it's open circuit. This is an open circuit terminal, right? So there's no current coming from your sensor. It's like this op-amp is measuring your input's voltage, right? Merely measuring the input voltage. It's not drawing power from it, not drawing current from it, right? So, and the current that's coming, feeding your load, is coming from the supply voltage, external supply, right? We drew this external supply circuit with a simple example with a transistor last time. Okay? So that's the benefit of the voltage follower circuit. You just want you want to transfer a signal from input to output, but the signal does not have enough power. It has a value, but no power. Right? It has a value of voltage, but no power. So you want to transfer it. That's the voltage follower circuit. So let's do a quick example. So we have a circuit here, and they would like you to calculate the voltage gain of this circuit under two conditions: the switch open and switch closed. Okay. So can somebody help me? How do I go about this? This is the same non-inverting amplifier we did before, right? So guys, come on. Let's look at the switch open case first. Okay, let's look at switch open case, and let's I have feedback. So is this negative feedback? Is this feedback driving the Vx to 0 or not? Let's look at that. Right? And if it's driving the Vx to 0, then we can learn a few things, and then we know that this is a open circuit, so this current is 0. I here equals 0 because this is like an open circuit coming into the op-amp. So we just want to make sure that Vx is equal to 0 as well, so that we can simplify our analysis. Right? So Vx is equal to what? The switch is open in this case. So forget about this for a while. What is Vx? Vx is the difference between the positive voltage and the negative voltage. And the switch is open. Is there any difference between the voltage? These two resistors are exactly the same. So if these two resistors are exactly the same, this voltage source is connected to the two resistors. So I'm driving Vx to 0. So Vx is equal to 0. Do you agree? Vx is equal to 0 in this case? Switch is open. Okay? So if Vx is equal to 0, what does that mean? This is Vx equal to 0. It means that I can, take a loop here. A switch is open. If the switch is open, I can take a loop where? This is 0. This voltage difference is 0. Then I can take, how about taking a loop here? This is open, right? So what can I do? And I know this current is 0, which means the current here is equal to the current here, right? Since the current here is 0. So how about I can take a loop around this loop? Right? This is one loop. How about, can I do this? Another loop, right? They shouldn't touch here. This is another loop, right? So I can write the equations for these loops as well. V input, I'll call this I1. I'll call this is I1 current flowing here, I2 current flowing here, and I3 current flowing here. I know that I1 is equal to I3. We agree? That's fine. And I know that Vx is equal to 0. These are things we established, okay, for the switch open case. Now what? Now let's do Kirchhoff voltage law around the loop. There's one loop here, one loop to the top resistor, one loop to the bottom resistor, because I know Vx is equal to 0. Right? So V input is equal to what? V input here is equal to, this is current flowing in the resistor. So there's a voltage drop corresponding to that in this fashion, right? This is the positive terminal, negative terminal, right? So I just draw the arrow this way. Right? And then here, this current, we said I1 is equal to I3. So there's a voltage drop as well this way across this resistor. And then this is my output voltage. Current is flowing in the resistor this way, and the voltage drop is here, V output. They define the polarity of V output here. Okay, so I can write my equation as what? V input is equal to I1 times R plus I3 times R plus V output. Or I can write it as I2 times R, the second loop. I2 times R plus I3 times R, right? This is my loop. Right? I know this voltage is 0, so I'm not going to put it here. Right? So I3 times R plus V output. What does this mean? What does this tell us about I2? Yeah, it's equal to I1. So I1 is equal to I2 and equal to I3, and what else does it tell us? What else do we know? What else do we know? We know that the current coming into the op amps, any current coming into the op amp is 0. So what does this tell us about the current at this terminal? Since I don't have any resistors here, right? What does, remember the op amp circuit looks like this. So what do I know about? So I know that current coming in here is 0, right? What does this tell us about Kirchhoff current law at this node? Kirchhoff current law at this node is I1 is equal to, so I1 is coming into the node, and I3 is coming out of the node, is equal to 0. How about Kirchhoff current law at this node? Current in this node is 0 since this is an op amp, right? I2, and then this is an open circuit, right? So I2 is equal to 0. So I2 is equal to 0, and I know that I1 is equal to I2 is equal to I3, and I know I2 is equal to 0, so these are all equal to 0. So what does this tell us about this equation? This is 0, this is 0. Tells us that V input is equal to V output. So it's like the voltage follower circuit, right? So this is a circuit with a voltage gain equal to 1. And an input impedance equal to infinity. Remember, input impedance was the input voltage divided by the input current. Input voltage divided by the input current. So remember, we used to calculate the input current by taking this input voltage divided by the impedance here, the resistance here. But here the resistance, it's an open circuit, right? So it's the voltage divided by a very large number, right? So there is no input impedance. The current will be 0. Current is 0 means the input impedance is very large, right? So that's why our input is equal to infinity. Okay with this? So are we okay with the first case? Now second case, this is connected. So let's analyze second case. Second case, this is connected. If I connect this, things are easier. So a lot of things don't change. Right? A lot of things don't change. The feedback is still there. So if the feedback is still there, then this Vx is still driven to 0. Okay? Since I have the feedback. If the feedback is there, the Vx is driven to 0. And since the feedback is there, also this current, and since it's an op amp, then this current is equal to 0. So the current here is equal to 0. There's no current coming into the op amp. Okay? So now what? So Vx is equal to 0. I input is equal to 0. So what is I input here? I input is equal to V input. Remember, this is a loop. And this is a loop. Right? So what is I1 equal to? This is I2, this is I3. So I know I1 is equal to I3. Right? What else do I know? I know that I input is equal to what? I1 plus I2. This is coming into the node. These are coming out of the node. So I input is equal to I1 plus I2. Right? So, so what is I1 equal to? I1 is equal to this voltage. Remember, I go around this loop here, outer loop. So it's equal to V input divided by R. I2 is equal to V input also divided by R. So this is IN. Right? So it's 2V input divided by R. So what else do they want? They want what else do we know about the circuit? Remember, we can take a loop here as well, right? This is the output. I can take a loop around this path. We take a loop around the input, and we take a loop around the output, right? So what does this loop tell us? This current is flowing here, I3. The voltage drop corresponding to that has a polarity in this direction. This is positive, this is negative. Correct? So, and then this is 0. The voltage here across here is 0. So I know that V output plus I3R is equal to 0. So V output is equal to minus I3 times R, and I3 is equal to I1 I3 is equal to I1, which is V input over R, minus V input over R times R. So what is the gain of this circuit? Before, the gain was what? When the switch was open, the gain was 1. Now the gain is -1, right? Because V output over V input is the gain. It's equal to -1. V output over V input is equal to -1 in this case. So the circuit has a gain of 1 before, and now it has a gain of -1 just by changing the switch. Okay? So it's a circuit to flip polarity of a signal. Any questions? Okay. Okay. Integrators and differentiators. What else can you do with this op-amp circuit? Let's see. So, same thing we discussed. We'll apply here, but we will get something neat as a result. So remember before I had what? I had a resistor in the feedback. I had this was my input resistance. I had a negative here, a positive here, and this was connected to ground, and this was connected to the input, and this was connected to ground. This was R, we call this I input. This was my open loop configuration. This is what this looks like, right? Open loop. And this is Vx. Vx is here. Vx is equal to what? 0, positive voltage on the positive terminal minus the voltage on the negative terminal. Voltage negative terminal is V input, right? So 0 minus V input. So it's a negative number. What does that tell you about the open loop gain? The open loop gain will be a large negative number. So I need to provide feedback, right, so that I fill in the space of this 0. So I will provide feedback here. I provide negative feedback. Why? So I know that the output is a large negative number, right? So the output is a negative number. We've established that the output will be negative, okay? Do we agree with that? So if I've established the output will be negative, how do I make Vx go to 0? I make Vx go to 0 by either replacing this 0 with something equal to V input, or I can have 0 minus V input altered by something else, by a large negative number, by something equal to V input. So if I do that, I make this go to 0. Yes, no? So I will feedback a negative number to this terminal. This is like having two voltage sources connected to this negative terminal here. Right? It's like having another V input here. Right? So then Vx is going to equal what? Vx is going to equal 0 minus the effective voltage around this loop. This loop has a voltage around this loop that we can control. We can control the voltage around this loop. We can control the voltage at this point. How can if I have a voltage source here, a resistor here, a resistor here, another voltage source here. That's what this looks like, and this is the voltage at this node of interest. This is the voltage at this node of interest. If I choose these two sources to equal and oppose each other, right? This is a positive voltage, like this one, a positive voltage, and then I make this a negative voltage, right? Meaning I feed back a negative number, right? If I feed back a negative number here, it's a voltage source that will oppose. This will be positive, negative, negative, positive. It will be a voltage source that will oppose the work of the other voltage source. Right? If I'm able to oppose the work of the other voltage source, able to oppose the work, sorry, it will be opposing it. Opposing it means it will put current in the opposite direction. So it will put current in the opposite direction as this source. So this source is trying to push current this way. This source is trying to push current this way. Right? I can select the values of resistors around the switch or the components around the switch such that I make these sources oppose each other and hence have no current flowing in the circuit. If I have no current flowing, then I can make this voltage, for example, equal to 0 because it's going to be equal to this node's voltage. This is the only defined voltage in my node, in my circuit. So I can control that. Yeah. So basically the whole idea is I was able to drive Vx to 0. By feedback, with feedback here of the resistor, I was able to drive the Vx to 0. If I'm able to drive Vx to 0, then what did we say we can do? Vx equals 0. Then this current is equal to, I know this current is equal to 0 because this is my op-amp's open circuit terminal. Right? If this current is open to this open circuit terminal, this is Vx equal to 0, then I can start doing my loop. Right? As soon as we have Vx equal to 0 and I know that this current input is equal to 0, then I can start taking a loop here. I can start taking a loop around here if I wish. Right? I can take a loop here if I wish, whatever I want. Right? So I can start taking loops after I define the voltages around the circuit. Right? So how does this help us with this circuit? If Vx is equal to 0, what is V output equal to? Remember, current is going in. This is I input current. Input current is flowing through this resistor. Where is it going to flow? I've replaced this feedback resistor now with a capacitor. Does not matter. It's a component that brings back part of the voltage. Right? So I've replaced the feedback resistor with a capacitor. So part of the voltage is being fed back here. But what matters is current here is 0. Vx is 0. That means what is the current here is equal to I input. If the current here is equal to I input, so I have the current flowing through the capacitor, and I have the voltage across the capacitor equal to Vc. Also, since Vx is equal to 0, then I can take this loop here. If I take this loop here, this V output, this is current flowing in the capacitor, will cause a voltage drop in the opposite direction, right? And then this Vx is 0. Right? So if I go around this loop here, what do I have? I have V output is equal to, or V output plus Vc is equal to 0. V output plus Vc, they're in the same direction, is equal to 0. So V output is equal to minus Vc. What is Vc equal to? IC is equal to C dVc by dt. Vc is equal to 1 over C integral of IC dt. Right? So the current that's coming in, I integrate, divided by capacity, that's Vc. Right? So it's, what is the current that's coming in? What is IC? This IC is the same as I input. I input is equal to what? V input over R, right? So I replace this inside this integral. I put V input over R, right? So V output is equal to minus V input over RC integration of I input dt. That is V output. So V output over V input is equal to minus 1 over RC integration of Sorry, what did I do? Yeah, sorry. It's I input is V input over R. There's no I anymore. I is the V. Sorry. Let me refresh. Guys, come on, quickly. So we have, this is current here. I input is equal to what? V input over R. Okay? And if I go around this loop, and I know this Vx is equal to 0, I know that V output plus Vc is equal to 0. So V output is equal to minus Vc. So Vc, and I know from the identities of the capacitor, is equal to 1 over C integral of IC dt. What is IC? IC is equal to I input. So it's 1 over C integral of V input over R times dt. So V output over V input is going to equal 1 over RC integral of V input times dt. So what did this circuit do? It minus 1 over RC, because there's a minus here, right? Minus. So the output of V input minus 1 over RC integral of V input dt. So it integrated my input voltage. Everybody's okay with this? Same approach, but let me swap the capacitor and resistor. Right? I'll swap the capacitor and the resistor. What do you think is going to happen? The exact opposite. Okay? So it will be a differentiator. So let's swap them. And go back to try to analyze quickly. So again, as long as I have feedback, if I have, this was 0 minus V input, right? 0 minus V input is Vx. Vx was an open loop. An open loop, the Vx is equal to 0 minus V input. So it's a large negative number. So I bring my feedback to the negative terminal. If it's a large positive number, I bring my feedback to the positive terminal. Right? So I brought my feedback back to the negative terminal. If I do that, what does that mean? That means that I'm driving Vx to 0. So I drove Vx to 0. And this current is equal to 0 since it's an op-amp, ideal op-amp. Right? Then we go through the same analysis. What is I input equal to? This is I input, or I1. I1 will also flow through this resistor. Since this current is equal to 0, this current will just flow in this resistor. Right? So, and then there's current flowing here, so there's a voltage drop across it here. This voltage plus this voltage is equal to 0 since there's nothing here if I go around this loop. So what does this mean? It means that V output is equal to minus I1 times R. What is I1? Is the current flowing here. It's the current flowing to the capacitor when I put a V input and a voltage input V input over it. So IC is equal to C dVc by dt. So it's equal to C dV in by dt. So substitute it here. So V output is equal to minus RC dV in by dt. Okay? So the output is a differentiation of the input. So minus RC dV in by dt. So before you leave, let me just, again, there's just one example about this, guys. So we derived the differentiation. This is the integration, not the differentiation, right? So if I have, I will just do this graphically, and then you can look at the solution here. So if I have a pulse, what is the integration of this pulse? There was no pulse before. I started at 0. The integration started at 0, the reset before. This is the reset switch. if I put this is if you do the calculation, if you put R feedback equal to 0 in the non-inverting amplifier, the output will be 0. So I start with an output of 0. If you have a pulse, what is an integration of a pulse? Integration of a fixed value is what? What's integration of a fixed value? Integration of 5, a slope, right? So the integration of this will be a slope. How about if I put another pulse? How about from here to here? Is the value going to change of the output? It will not change. Here, you see another slope. Do you agree? So what they're asking for here is, and this is if we look at the output, it's a negative output, right? So they're asking you how many pulses is required to bring the output voltage to minus 10 volts, knowing that each of these pulses has a magnitude of 5 volts and duration of 2 milliseconds, right? So they're asking you to integrate a fixed value of 5 for 2 milliseconds. Basically calculate this area. So it's 0 at the beginning. At the final value is the value of the area under the curve. And then it's fixed, and then it steps up again by the same amount, area under the curve. Okay, so that's this example. They tell you that the solution is what? 5 pulses. There's 20 pulses are required to produce minus 10 volts. So each pulse is going to produce minus half volt. Any questions on this? Please go through the example. So this wraps up this chapter, guys. But this chapter, as I said, is not in the exam.